Welcome to another podcast. This episode we're going to be taking a look at what's called a spiral system or spiral critical point behavior of a planar system. For this example, we have a coefficient matrix of the form -1, -1, 2, -3. And so this is going to lead us to a characteristic polynomial of the form lambda squared plus 4 lambda, and here the determinant is 3 minus a -2, so it's going to be a plus of 5. And if you look at this one, we're not going to be able to factor this, so I'm going to have to resort to the quadratic formula here. And so if you look at that, that looks like it's going to be -2 plus or minus I. And so what we have here is we have a complex conjugate pair. Lambda 1 is equal to the conjugate of lambda 2. And the other thing I want you to notice is that the real part of the eigenvalues here is equal to -2. Both of them have real part -2, and that's less than 0. And so we're going to look at the effect that has. Now, without going into the full eigenvalue method to find the solution here, we can at least talk about what the solution is going to look like. So based on our previous experience, if we were to spend the time solving this completely out, what we would end up with is a C1 times a bunch of stuff, and then the fact that this is -2 would mean they'd all be multiplied by e to the -2t, plus C2 times a bunch of stuff. Once again, it would be multiplied by e to the -2t. Now the question is, what is the stuff? Well, you know when you get complex roots, it's the imaginary part of the root, so this fact, the imaginary part's 1, that controls the frequency of the rotation. And so we would have a vector here, a1, a2, corresponding to cosine of t, and then you would also get another linear combination of sine of t. And then similarly here, I would end up with a, let's say, a d1 and a d2 cosine of t, plus a e1 and e2 sine of t. So I ran out of room there a little bit. Let's see if I can make that look a little bit better. So sine of t, and then all of this is times e to the -2t. So that's what our system looks like, and that's what our solution looks like. And what I want you to recognize here is that the e to the -2t's are going to bring everything to 0. In other words, the behavior that I have here is the solution x of t converges to 0 for all t as t goes to infinity, and it converges to infinity. Well, the absolute value goes to infinity as t converges to -infinity, which means that going forward in time, everything collapses to the middle, and going away from the middle, you're moving backwards in time, and therefore everything goes away or emanates from the middle. And so what you have to keep in mind here is that we still have this nice sort of sinking behavior here. So the fact that these are e to the -2t's means that we're going to experience this sinking behavior. Everything's going to sink into the origin. But the question is, what do the cosines and sines bring to the picture that we hadn't experienced before? And you're probably familiar with cosine and sine as being periodic, and when you add them together in a plane like this, you get what are called rotations. So these are going to add rotations to the mix. And so what you have to end up deciding is it a counterclockwise or clockwise rotation that takes place? And so the best way to describe this is to check out a single point. So for example, if I look at the original system and I say, okay, what happens when we're looking at the point xy equal, let's say x is 1 and y is 0. Then our system becomes x prime y prime equals, well, if I plug those in, so if x is 1 and y is 0, I get negative 1 and 2. Just read off the coefficients here from the first column. That's what you get. Well, what direction? So this says, okay, this says I'm starting at the point 1, 0, and my derivative vector, which would be my tangent vector to the curve at that point, is pointing in the direction negative 1, 2. So the tangent to the curve at that point is pointing in this direction. This suggests that the rotation is clockwise, or counterclockwise. If it had been pointing down, then we would know that the rotation is clockwise instead. So it's rotating from right to left, and it's sinking into the origin. Putting all of that together, then that gives us sort of a clear picture here that the curve that starts here has to be doing something like this. Its tangent is the vector negative 1, 2, but it sinks into the origin. And as it gets further away, it spirals out. So just think of it this way. Things come in, they spiral out. Things come in, they spiral out. Things come in, they spiral out. They come in, they spiral out. This is the picture that's being described here. So this is the behavior that's being exhibited, and what we know is all of these are collapsing to the origin, so the direction of the curves here is coming into the origin. So the solution behavior that's being described here, and remember, these would keep rotating on. So you would see this nice rotation behavior in the plane from each of these trajectories. So this behavior is called a spiral sink. The spiral part's fairly obvious. The spiral part comes from the rotations that are exhibited by the cosine and sine. We know that the rotation here is counterclockwise, looking at this vector that we plotted. We could plot another vector over here and see that everything's pointing back and up. And so things have to be tangent going in that direction. So that tells us that we have a counterclockwise rotation and everything's coming into or collapsing into the origin. So the fact that it was a sink is because the real part was negative. If the real part had been positive, so the real part of lambda was negative, caused this. If the real part of lambda had been positive, then you would have what's called a spiral source. And if the real part of lambda is 0, let's talk about that for a second. If the real part of lambda is 0, then you're rotating, but you're never getting any closer to the origin. So let's think about that for a second. You start to rotate, but you never get any closer to the origin. Think of it sort of as gravity. You're never going to get any closer than when you started. The best way to describe this is like this. You end up with something that is elliptical in nature. And so this corresponds to the kind of solution you would expect to see if the real part of lambda is 0. In other words, if you ended up with purely imaginary roots. If that happens, then over time you don't have these e to the negative 2t's. All you have is linear combinations of cosine and sine, and linear combinations of cosine and sine in the phase plane are either ellipses or circles. And so the behavior associated with the real part of lambda being 0, in other words, we have purely imaginary roots, so purely imaginary eigenvalues, is associated with what's called a center point behavior. And there is neither sink nor source associated with that name, so they're just called center points. And so rather than having everything spiral in or out, you just stay with basically these concentric circles, or concentric ellipses, if you will. So something like this. So this is called center point behavior. You get behavior similar to this. All right, we've described all of the important cases at this point with nodes, with saddles, and with spirals. In the next video that we're going to look at, we're going to try to put it all together and describe a general theory of what's happening here. All right, thank you for watching.